Good morning students, myself Purnima, and you have attended my lecture number 1 of the structure of atom. Now I'll teach you more about the structure of atom. In last period we have studied about discoveries of electron, proton and neutron, different models. Earliest model we had discussed about Thomson model and drawbacks. We had discussed about Rutherford and drawbacks. Bohr model we had discussed, and EMR, electromagnetic radiation. Now in this lecture we'll revise the Bohr model. Some important postulates we'll revise, and the second thing that dual nature of electromagnetic radiation, photoelectric effect, black body radiation and spectrum. So this chapter is very important, and all the topics are very important, theoretical. You learn them very easily, so better try to be serious with your study. So according to Bohr model, we can see the figure that electrons, they are in concentric circle, and the electrons are revolved, and they have the shell number 1 and n is the shell number. And according to Bohr, the electrons revolve around the nucleus in concentric circular orbit situated at fixed distance with fixed energy. They are stationary, means the orbits, they do not move, only electrons revolve, and while revolving electrons do not radiate any energy. And third, the most important, the electrons revolve in those orbits for which the angular momentum is integral multiple of h by 2 pi. Students, please learn it very properly. The electrons revolve in those orbits for which the angular momentum is integral multiple of h by 2 pi. Now first you know that what do you mean by angular momentum. Children, in class 9th you have already studied about momentum, which is represented by P is equal to mass into velocity. But as the electron revolves in circular path, so the angular momentum for circular path is equal to mvr. We have to multiply mv with radius. So mvr is equal to n h by 2 pi, where n is the shell number 1, 2, 3. It means if we talk about the shell number 1, n is equal to 1, so the angular momentum of shell number is h by 2 pi. If we talk about n is equal to 2, then is equal to 2 h 2 pi. Okay, it does not like 2.5, 1.5, no, it is in the integral multiple. Next, energy goes on increasing. Stationary orbits goes farther from the nucleus. We will discuss this point in spectrum. And the most important, which Bohr was given, that a definite amount of energy or quantum energy is absorbed when electrons jump from lower to higher energy level. When electron jumps from lower to high energy level, because it absorbs the energy, and this condition is called quantization condition, which was a we can say improvement in Rutherford model and given by Bohr model. But children, you know, electron always try to remain in lower energy level, as like we always remain in the comfort zone. Just like that, electron has the comfort zone to remain in the lowest energy level. So when the electron returns back to its lower level from the higher one, it emits energy in the form of electromagnetic radiation. Students, we have studied about the electromagnetic radiation in last period, means period number 1. Now the next topic is electromagnetic spectrum. There are many types of electromagnetic radiation, which differ from one another in wavelength and frequency. You all know wavelength and frequency. We had discussed in the last lecture. These constitute what is called electromagnetic spectrum. An example, that the radio frequency region around 10 to the power 6 hertz used for what? Broadcasting. Microwave region around 10 to the power 10 hertz used for radar. Infrared region around 10 to the power 13 hertz used for heating. So different regions are there, different frequency they have. Basically electromagnetic spectrum is a continuous spectrum, and it consists of a range of electromagnetic radiation which arranged in the increasing wavelength or decreasing frequency. If the wavelength decreases, what will happen? Decreasing frequency. It extends from radio waves to gamma rays. The small portion around 10 to the power 15 hertz. Okay, listen it carefully. The small portion around 10 to the power 15 hertz is ordinary, we can say, visible light. We can visible it. It is only this part which our eyes can see. Otherwise, special instruments are required to detect non-visible radiation. We can't detect them. You can see the spectrum 10 to the power 15, that visible spectrum you can see. Otherwise, gamma rays, X-rays, UV rays, infrared, microwave, FM, AM, we cannot visible them. So special instruments are used for that. Students, Bohr explained the wave nature of electromagnetic radiation through diffraction and interference. In diffraction and interference can be explained the wave nature of electromagnetic radiation. But some of the observation which could not be explained, that first is the nature of emission of radiation from hot bodies. We call it black body radiation. Second, ejection of electron from metal surface from radiation strikes it. When radiation strikes it, and it is called what? Photoelectric effect. Then third, variation of heat capacity of solid as a function of temperature. And fourth, line spectra of atoms with special reference to hydrogen. So these four observations could not be explained by the wave nature of electromagnetic radiation, and that is why the particle nature of electromagnetic radiation explained. The first explanation for the phenomenon of the black body was given by Max Planck in 1900. He proved that when solids are heated, suppose for example when iron rod is heated, it first turns to dull red, then becomes more and more red as the temperature increases. And what will happen when we as this heated further, it becomes white and then it becomes blue as the temperature becomes very high. It means that the frequency of emitted radiation goes from a lower frequency to a higher frequency as the temperature increases, because the red color lies in the lower frequency region while blue color belongs to the higher frequency. So he said that an ideal body which emits and absorbs all frequency is called a black body. The radiation emitted by such a body is called black body radiation. He also suggests that atoms or molecules could emit or absorb energy only in discrete quantities, and he gave these discrete quantities as quantum. So he explained that at a given temperature, intensity of radiation emitted increases with decrease of wavelength and reaches a maximum value at a given wavelength and then start decreasing with further decrease of wavelength. So according to Planck's quantum theory, the radiant energy is emitted or absorbed not continuously but discontinuously in the form of small energy packets, which is called quantum. This is in case of, we are talking about electromagnetic radiation. But in case of light, the quantum of energy is called what? Photon. The energy of each quantum is directly proportional to the frequency of the radiation, means E proportional to nu. Nu is for frequency. E is equal to h nu, where h is the Planck's constant and its value is 6.626 into 10 to the power minus 34 joule second. Energy is always emitted or absorbed as integral multiple of this quantum, means E is equal to n h nu, where n is equal to 1, 2, 3, 4, whatever it is. Now through this graph you can see that with this theory Planck was able to explain the distribution of intensity in the radiation from black body as a function of what? Wavelength or frequency at different temperatures. So now the next phenomenon, photoelectric effect, in this you can see the figure 19 hertz. You know, hertz is famous for the unit of frequency also. So Hertz performed experiment in which electrons ejected when certain metals, like we can say alkali metals, potassium, rubidium, cesium, were exposed to a beam of light. What will happen? Electrons ejected, and this phenomenon is called what? Photoelectric effect. Then he observed in experiment that when a beam of light falls on a metal surface, electrons are ejected immediately. You know, this number of electrons ejected is proportional to the intensity or brightness of light. If the intensity increases, the number of electrons also ejected increases. The term which was given by the this scientist, that is threshold frequency, which is represented by mu 0. For each metal there is a characteristic minimum frequency below which photoelectric effect is not absorbed, means the ejection of electron is not absorbed. This is called what? Threshold frequency. If frequency of light is less than the threshold frequency, there is no ejection of electrons, whether the intensity is high or whatever it is. It falls on the surface or how it is its intensity, it does not depend. It only depends on threshold frequency. You can see the figure that the light beam of light on surface of metal, then what will happen? Photoelectron energy is equal to light energy in and minus binding energy, and this energy out in the form of kinetic energy. So this through this figure, this picture, you can easily learn the thing that photon of energy E heads towards an electron of them on the metal surface. But what will happen? Energy of photon with frequency S head towards E is equal to Hs, and the photon will eject the electron from the surface. It has energy bigger than the work function. Now what do you mean by work function? This is the minimum energy needed by an electron to escape the metal, and it is called what? Work function of the metal. And the third one it is explaining. This is electron and this is one. Third is the ejected electron is called a photoelectron. It will have kinetic energy given by this Ek is equal to Hf. F is for frequency, or mu we can say, minus mu 0, E0 for that. F0 it means it is the minimum frequency, we can say threshold frequency of a photon of light that will eject an electron from the metal, linked to the threshold frequency. The work function is linked to the threshold frequency. Photoelectric work function W0, the minimum energy required to eject electron. Minimum energy required to eject electron is called what? Photoelectric work function, which is equal to h mu 0. Energy of the ejected electron H is common, H nu minus H nu 0 is equal to half mv square. Now the dual behavior of electromagnetic radiation. Now Bohr explained both particle and wave-like properties. For wave property through diffraction and interference, but for the particle-like properties, black body radiation and the photoelectric effect. Now the next topic is atomic spectra. You all know that speed of light depends upon the medium through which it passes, and it may be deviated or refracted when it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave of shorter wavelength bends more than the one with the longer wavelength. Now, what is spectrum? When a white light is passed through a prism, it splits into a series of color bands and it is known as spectrum. A spectrum is of two types: continuous spectrum and line spectrum. Continuous spectrum, the spectrum which consists of all the wavelengths, is called spectrum. In continuous spectrum, the spectrum of white light which we can see ranges from violet to red. Such a spectrum is known as continuous. Continuous because violet merges into blue, blue into green, and so on. A similar spectrum is produced when a rainbow forms in the sky. Because as we know that electromagnetic radiation, when interacts with matter, atoms and molecules, they absorb what energy and reach it to the higher energy state, and which is unstable for them, and for returning to their normal or more stable phase, what will happen? They radiate what? Electromagnetic spectrum. And the second is line spectrum. Line spectrum, a spectrum in which only specific wavelengths are present, is known as line spectrum. It has bright lights with dark spaces between them. We can say that the spectrum which can be identified by the appearance of bright lights in the spectrum. You can see the figure that continuous spectrum show all wavelengths of visible light, whereas absorption line spectrum, black lines on colored background on black lines on colored background. Children, spectrum is also classified as emission and line spectrum. Emission spectrum, we can say the spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Students, atoms, molecules or ions that have absorbed radiation are said to be what? Excited. To produce an emission spectrum, energy is supplied to a sample by heating it, and the wavelength of the radiation what? Emitted. But in case of absorption spectrum, is just like photographic negative of an emission spectrum. I am repeating, it is just like a photographic negative of an emission spectrum. Or we can say a continuous of radiation is passed to a sample which absorbs radiation of certain wavelengths. The wavelengths which are absorbed are missing and come as dark lines. And the study of emission or absorption, both spectra, is referred to the spectroscopy. You can see continuous spectrum, emission spectrum and absorption spectrum. Bulb passes through the prism, then we can say continuous spectrum. In case of gas, hot gas, we can see emission line spectrum, and in case of cold gas, we can see absorption line spectrum. So line emission spectrum is used in the study of electronic structure. Each element has a unique line emission spectrum, and this characteristic line is used in chemical analysis. Just like fingerprints are used to identify people, we can identify people or a single person by the with the help of fingerprints. Just like that, they have characteristic line spectrum to identify unknown atoms. The element helium was discovered in the sun by this method only, that is called spectroscopic method. Now, line spectrum of hydrogen. When an electric discharge is passed through a gaseous hydrogen, the molecule dissociates, and the excited hydrogen atoms produce what it emits radiation. It emits energy, which produce what electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of series of lines named after their discoverers. This is a new line is for it is used for wave number, which is equal to 109.677 bracket close 1 upon n1 square and 1 upon n2 square, where n is equal to 1, 2, 3 again. Now this formula is first used described for the Balmer series. The series of lines described by this formula are called Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region. But Johann Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expression, the same formula. And the value of Rydberg constant for hydrogen is 109.677 per centimeter. So the first 5 series are Lyman, Balmer, Paschen, Brackett and Peatman. So these are the series of the line spectrum. Of all the elements, hydrogen atom has the smallest line spectrum. Line spectrum more and more complex for the heavier atom. So the line spectrum of element is unique, and there is regularity in the line spectrum of each element. So this is the transitions of the electrons in the hydrogen atom. This diagram shows the Lyman, Balmer and Paschen series of transitions, in which electron will move from a lower stationary level to a higher stationary level. State that when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower energy state. The energy change does not take place in a continuous manner. So this is Rydberg's equation. Through he could be described by the he could be described all series of lines in the hydrogen spectrum. Wave number is equal to 109.677 bracket 1 upon n1 square minus 1 upon n2 square per centimeter. R is for Rydberg constant, and its value is 109.677 per centimeter. So students, learn these all the we can say equation as well as effects, photoelectric effect, black body radiation, spectrum, different type of spectrum, and the series. So all important Bohr models, you learn them very sincerely. Thank you.